In this lecture, I will discuss the four main states of matter, as well as some quantities that are used to describe matter. Matter is made out of combinations of elements. There are approximately 100 elements in existence that we know of right now. And so substances are made of combinations of those elements. Since the number of combinations that are possible is essentially indefinite, we have a giant variety of substances or matter in the world and the universe in existence today. However, the variety of combinations can be divided into four basic forms or states. So the states or forms of matter are as follows: solids, liquid, gas, and plasma. I will discuss each of those states separately, but before I start a discussion of the properties of solids, liquids, gases, and plasma, let's first talk about the building blocks of matter. Atoms are the building blocks of matter. The structure of the atom can be described in the simplest terms as the structure of the solar system. We have one central object, which is called the nucleus, in which we have two types of particles confined, and then we have the electrons which orbit around the nucleus, just like the planets. This is a simplified view of the structure of the atom, but for the purposes of visualization, this is the most convenient version to use. So we have the nucleus, in which we have two types of particles. We have neutrons, and then we also have protons. And the number of neutrons and protons depend on the specific element to which this atom belongs. And then around the nucleus, we have electrons that orbit in circular orbits. And as I said, this model is very similar to the model of the solar system. As a matter of fact, this model is known as the planetary model of the atom. In reality, the picture is much more complex than that. Here are the electrons orbiting around the nucleus. And so, of course, depending on the atom or the element to which the atom belongs, the number of electrons also will vary. So we have atoms with 1 electron, and then we have atoms with 100 electrons. What keeps the electrons orbiting around the nucleus, like so? Now, one could say that would be the gravitational force between the electrons and the nucleus. However, this force is very, very small. There is a different force that keeps the atom together, and that is the electrostatic force of interaction between charged particles. So the electrons are charged particles, and so are the protons, while the neutrons are not electrically charged. And so the electrons and the protons, turns out, are charged oppositely, and therefore there is an attractive electric force between the electrons and the protons, which causes the electrons to orbit around the nucleus. This force, the electric or the electrostatic force between the electrons and the protons, is actually extremely important because If this force did not exist or ceased to exist, then the atoms will not be having this structure. The electrons will be just floating in space, and the protons as well. There will be no interaction between the two. And essentially, all matter will become a soup of electrons and protons without actually forming any substances. So let's summarize the information about the protons, neutrons, and the electrons. So the protons are positively charged. The electrons are negatively charged. And finally, the neutrons are not charged. Each element is made of arrangements of its specific atoms, and the atoms of the elements have unique number of protons and electrons, and there are no two elements that have the same number of electrons and protons. Any isolated atom has equal number of electrons and protons. Many of the elements in existence have also isotopes. What is an isotope? Isotopes of elements are forms of those elements made from atoms with the same number of electrons and protons, but different number of neutrons. Let me give you several examples of isotopes of known elements. First, we have protium, which is the most common form of hydrogen, and this has 1 proton, 1 electron, and 0 neutrons. And when we talk about hydrogen in general, we refer to that form, and so we write this as H2. The second isotope of hydrogen is deuterium. This is a rare element on Earth, and the structure of the atom is 1 proton, 1 electron, and 1 neutron. And the last isotope of the hydrogen is tritium, which has trace amounts on Earth. It is radioactive, and the structure is 1 proton, 1 electron, and 2 neutrons. So you see how just the difference of 1 neutron in each of those plays a huge difference in the availability on Earth and also some of the properties, such as radioactive versus non-radioactive. An important physical property of matter is density. Density is a very convenient property that can be used to identify different elements and also substances, because density is a unique property for those materials, for those substances, and for those elements. Density is defined as the ratio of mass and volume of the substance or element from which an object is made. Density D is equal to the mass of the object divided by the volume of the object. So M is mass and V is volume. There are several acceptable units for density. However, in the metric system, the base unit will be kilograms divided by cubic meters. However, other units that we will encounter are, for example, grams per cubic centimeter. And in the imperial system, it's going to be slugs per cubic inch, for example, or per cubic foot. I'm not going to list those since we're working in the metric system. So the units here tell you that, since we are working in the base units, tell you that when you are calculating density, you must convert the mass in kilograms and you must convert the volume in cubic meters. So why is density a unique quantity that can be used to identify various elements or substances? Because no matter how big the mass of the object in question is, that will, of course, also reflect on the volume of the object, but the ratio of the two will always be constant. So, for example, 1 gram of gold coin has the same density as a 1 kilogram of gold block. So a gold coin with mass of 1 gram has the same density as a gold block of mass 100 kilograms. Clearly the masses are way different, the volumes will be also way different, but the density, the ratio of mass to volume, will remain constant. Let's do the following example using the definition of density. An aluminum ingot is 3 meters long, 1 meter wide, and 0.3 meters thick. If the ingot has a mass of 2,430 kilograms, what is the density of aluminum? So here we know the dimensions of the ingot, and this is essentially a rectangular prism, something like this. So we know the length is 3 meters, the width is 1 meter, and then the height is 0.3 meters, or the thickness. So the volume is calculated as the product of length, width, and height. So this will be 3 meters times 1 meter times 0.3 meters, which is equal to 0.9 cubic meters. We also know the mass of this ingot, and that is 2,430 kilograms. So then the density is the mass divided by the volume, which will be 2,430 kilograms divided by 0.9 cubic meters. And this gives us 2,700 kilograms per cubic meter density. If I wanted to present this in units of grams per cubic centimeter, that simply becomes 2.7 grams per cubic centimeter. The density of elements and substances varies a lot. Let me give you two values just to show you how much of a difference we can have for the same amount of material. The density of water is, for a cubic meter of water, the density is 1,000 kilograms per cubic meter. And that much water has a mass of 1 ton. Compare this to the density of osmium. A cubic meter of osmium has density of 22,480 kilograms per cubic meter and a mass of 22.48 tons in the same volume. So a cubic meter of water has a mass of 1 ton. A cubic meter of osmium has a mass of 22.48 tons. Osmium is one of the heaviest elements in existence that we know of. Now let's start the discussion on the 4 main states of matter. The first state of matter that I want to talk about is solids. Solids have the greatest variety of properties of the 4 states of matter. The properties are determined by their atoms and how they are arranged. In solids, the atoms arrange in repetitive patterns called crystal lattice. Solids exhibit crystal structure. An important class of solids are metals. In metals, the atomic arrangement is symmetric, and as I already mentioned, is called a crystal lattice. The smallest building block of the crystal lattice is a cell made by atoms arranged in a specific way, and that specific way is unique for each different metal. So in metals, the atoms form cells. Those are the smallest building blocks of the crystal lattice of the metal. Different metals have different atomic arrangements, therefore the cells look different, and therefore the crystal lattices for different metals look different. So let's give an example with a simple crystal lattice, which will be made from cells that have the shape of a cube. And thus this type of crystal lattice is called cubic lattice. So we have the atoms arranged at the tips of a cube. The dotted lines represent the force interactions between the atoms. You can think of those force interactions as tiny springs that connect the atoms in this cell. Okay, so now a crystal lattice is an arrangement of cells which is periodic in all three dimensions. So for example, I can take this cell and multiply it to the left, up and down, and that is going to give me the crystal lattice of that particular type of metal. So here is an example of a crystal lattice made from an arrangement of those cubic cells. And this crystal lattice is known as cubic. There are, as I said, many different types depending on the arrangement of atoms. This is one of the simplest ones. Because of the crystal structure of solids in general and the arrangement of the atoms in these symmetric and repetitive cells forming the crystal lattice, solids have their own shape and also fixed volume. So the existence of crystal lattice leads to fixed volume and defined shape for solids. And if you have seen cube of sugar, a single grain of sugar has also a cubic shape, and that is because the crystal lattice of sugar has a general cubic arrangement. So this is a simple example of the defined shape and fixed volume for solids. Depending on the arrangement of the atoms of the solid in the crystal lattice, we can have two different or three different or several different substances in existence made from the same atoms. The best known probably example of this property of solids is the arrangement of carbon atoms. Carbon atoms can arrange in two different ways in the crystal lattice, which produce a diamond or graphite. And those two substances have completely different properties. So here is the crystal lattice of a diamond. Each carbon atom is equally distanced from the other carbon atoms. And this provides a very strong connection or a very rigid structure to the crystal lattice, which then, as we know, makes diamond extremely hard. So the hardness essentially comes from the fact that it's very hard to remove an atom by mechanically dragging the surface of a diamond across another surface. Now let's look at the structure of graphite. This is an example of the crystal lattice of graphite. This basically consists of hexagons that arrange in planes that the distance between the planes is larger than the distance between the atoms in those hexagons. And so that makes it very easy to cleave the planes from the lattice of the graphite, because these bonds are weaker and are easy to break. And so when you are writing with your pencil on a piece of paper, the friction with the paper essentially cleaves those atomic bonds here, and you are leaving some graphite on the paper, and that's how you write. So as you can see, the same material, two completely different crystal lattices, which also lead to two completely different behaviors of those substances. The next state of matter that I would like to discuss is liquids. When a solid melts, the interatomic bonds break, allowing the atoms or molecules of the substance to slide over one another, producing a liquid. Liquids take the shape of their container and have fixed volume. So liquids take the shape of their container and also have fixed volume. Any solid can be converted into liquid when the correct temperature for the transition from the solid phase to the liquid phase is achieved. At standard atmospheric conditions, which means one pressure of atmosphere, 25 degrees Celsius temperature, some substances exist as liquids naturally, and then other substances exist as solids naturally. And the temperatures at which solids become liquids vary from material to material. For example, hydrogen melts at 14 degrees Kelvin, which is negative 434.47 degrees Fahrenheit. Water melts at 273 degrees Kelvin, which is 0 degrees Celsius or 32 degrees Fahrenheit, and so on and so forth. So the transition from solid to liquid phase happens at different temperatures depending on the particular substance. Hydrogen melts at negative 434.47 degrees Fahrenheit, and water melts, that means ice, melts at 273 Kelvin or 0 degrees Celsius or 32 degrees Fahrenheit. The opposite transition is also possible, that is the transition from liquid to solid phase, in which case, again, for the different substances and elements, the transition happens at different specific temperatures. Why do the transitions from solid to liquid or from liquid to solid state happen at different temperatures? Well, this is because of the structure of the solid. We already discussed the crystal structure of solids, and so the arrangement of atoms requires certain bonds to be formed, but those certain bonds can only be formed when certain temperatures are available. At other temperatures, those bonds cannot form, therefore the transition cannot happen. One characteristic property of liquids only is surface tension. And you have observed examples of surface tension. For example, a drop of water on a flat surface has the shape of a dome or partial sphere. If you look at the water in a glass, and you fill the glass with water more than, to above, the edge here, what you would observe is that the water will form this kind of shape. Then the question is, why does the water assume this shape? Why does it not just flatten on the surface here or spill from the glass here? Of course, if you keep on adding water to the glass, eventually it will spill. But you know that if you add more water than the glass can hold, just the reasonable amount, you are going to achieve this type of shape of the water above the glass. So why does it not just spill? This is because of surface tension. So what is surface tension? Okay, so the water is composed of molecules. And the molecules exert attractive forces on each other. So these molecules here on the very surface of the water, they exert attractive forces on each other. So they pull towards each other like this. And this is because of the tendency of liquids to try to assume the shape that seeks the state with the smallest surface area. And we know from geometry that the smallest surface area in existence is the sphere. So a sphere has the smallest surface area in existence. Okay, so the molecules here on the surface layer attract each other, which then results in this surface area of the surface layer to be the smallest possible in existence, which leads to the state with the smallest energy as well. Okay, but then we have molecules below the surface layer of molecules. So they will then attract the surface layer as well as they will attract each other. And so these attractions produce this sort of a net of all these attractive forces that connect all the molecules like this. And then that produces a very stable arrangement which, left on its own, is not going to change. And so this is, again, the result, or as what we know as surface tension. One more time, this is a property specific to liquids. To summarize, surface tension is due to the natural tendency of liquids to seek states with smallest surface area. The third state of matter is gases. Gases are formed when molecules separate completely and then a liquid turns into a gas. This, of course, transition happens when the proper temperature is reached for the transition. Gas is formed when a liquid is heated enough to break the bonds in the molecules of that liquid. Gases have no fixed volume, and also they do not have defined shape. They just take the shape of their container. Any gas can be described as a system of molecules or atoms, and the state of the system can be described by its volume, its pressure, and temperature. Depending on how the volume, pressure, and temperature change, the state of that system of molecules, of this gas, will also change. For example, if the volume is kept constant and the temperature is increased, then the pressure of the system will increase. An example of such situation would be a spray, such as a deodorant spray, placed in a microwave or on fire or heated up. What that means is that the volume is fixed, since the container defines the volume of the gas inside. The temperature goes up, the pressure will increase, and then an explosion can happen. Pressure is a very interesting quantity when related to the concept of fluids. First, what is a fluid? A fluid is any substance that is a gas or liquid. Now, we know that pressure is defined as a force divided by surface area over which the force was applied. So, for example, if you look at a block resting on a flat surface, the pressure that this block will exert on the surface will depend on the surface area which the block covers. So that will be the surface area of the base. And of course, the surface is flat surface. This is a perspective view. And the force that will be producing the pressure will be the weight of the block straight down, applied on the surface. So in this case, pressure here will be weight divided by the surface area, the weight of the block divided by the surface area of the base of the block. Okay. What happens when we submerge an object in a fluid? We know that that object will experience force and therefore pressure. So consider this our fluid. So in this example, that will be liquid, and it can be water, it can be anything, it doesn't matter. And here is the object. So this is a spherical object. It turns out that the force applied by the fluid comes from all directions. It does not come from a preferred direction. And so the force is equally distributed over the surface area of the object. So when calculating pressure, obviously, the same definition applies, force divided by surface area, with the difference between this case and the case of an object submerged in fluid is that the force applied by the fluid comes from all directions. What is the consequence of this effect here of the object submerged in a fluid? Well, for us, this is an interesting example. For us, we are walking on the earth. We are experiencing force applied to our bodies by the entire atmosphere of the earth. Not only from above or from the sides, but from every direction, the entire atmosphere of the earth. This is pretty hard to imagine. The value of the atmospheric pressure is approximately 14.7 pounds per square inch, or this is approximately 20 tons of pressure. This is giant. However, we have evolved, obviously, enough to really not feel it. When we have an object submerged in a liquid, the deeper the object gets under the surface of the liquid, the larger will be the force that the liquid will apply or exert to the surface of this object, the larger will be the pressure that the object will experience. However, if the object moves horizontally to the surface of the liquid, the pressure remains constant. This is extremely important to remember. As long as the object is moving horizontal to the surface of the liquid, the pressure will be constant. If the object changes distance from the surface of the liquid, the pressure will change. The object going deeper will result in more pressure. the object going shallower or closer to the surface will result in less pressure. A simple example to sort of help you visualize this statement is if you are swimming underwater. You know that if you start diving deeper, you are going to feel more pressure from the water surrounding your body. And you know that as you're coming closer towards the surface, the pressure that you're going to feel will decrease. The fourth state of matter that I'd like to talk about is plasma. Plasma is superheated gas. Plasma is superheated gas in which the molecules or atoms have split into positive and negative ions. So the temperature is so high that the atomic bonds in the molecules or the atoms that make the gas have been broken. And now we have positive and negatively charged particles, ions. Plasma is actually the most common state of matter in the universe. There is countless amounts of plasma in the universe, in the dark clouds, in the stars, everywhere. On Earth, plasma is observed in lightning discharges. So lightning discharges create plasma channels for superheated gas to flow. And as you know, lightning carries a large dose of electricity, and that is because of the existence of positive and negative ions in the plasma. Another example of the use of plasma is neon light tubes. So they operate by creating a plasma flow in the gas used in the tube. And depending on the type of gas or mixture of gases that's being used, that also determines the color that this light tube will emit. So we have white, we have green, we have red, we have purple. These all depend on the type of gas used in the tube. And with this, I will conclude the lecture on states of matter.